Okay, good evening and welcome back. Before I forget, I will give you this paper soon. If you couldn't register 2 weeks ago because I forgot to give you this, you can still do it. Or if you couldn't register last week, you can still do it. Just be correct and don't put marks everywhere. Okay, let me remind you what we were doing or what we have done last week. You remember we faced a problem. We wanted to discuss the Fourier transform of a distribution. The problem is the set of test function is not stable on the Fourier transform. If you take the Fourier transform of a test function, it's no more a test function. So we had to introduce something else. So we introduced a new space made of functions which they are decreasing very fast, faster than any polynomial, and their derivative also are decreasing very fast. It's called the Schwarz space. So it contains a set of test functions, but it's slightly bigger. And what we have seen is that this Schwarz space is stable on the Fourier transform. Maybe can you turn off your microphone thing? Except if you have a question. Yeah, thank you. Okay, this Schwarz space is stable on the Fourier transform, and this will be very useful. And we need a notion of convergence on this space, and I don't recall it completely, but this is the expression which appears. So the family of fj is converging to f infinity if when you take any derivative and when you multiply by any polynomial, it still goes to 0. The sup over all x, so the L infinity norm, is still going to 0. And now what is a tempered distribution? It's a function from this Schwarz space to K, so either R or C, which is continuous in this sense. Whenever fj goes to f infinity in this sense, then t of fj, this is just a number, goes to t of f infinity. We had something similar for the distribution, but now we have it for tempered distribution, but the convergence is slightly different. The set of all tempered distribution is S prime, okay, which is a smaller set compared to the set of distribution because you impose something stronger for the convergence. But now the good point is we can take the set of the Fourier transform of a tempered distribution. So for any t in this set of tempered distribution, I define the Fourier transform of t evaluated on the Schwarz function as t of ff. Why it's good? Because, as I mentioned, the set of Schwarz function is stable on the Fourier transform. So this is still a Schwarz function, and I can apply t. So I can give this as a definition of the Fourier transform. And it turns out that this Fourier transform of a distribution is, in fact, even bijective from the set of tempered distribution to itself. And why? What are the main applications of this? First, you need to check that delta 0, the Dirac delta distribution, is tempered distribution, but then we can take its Fourier transform and we get this distribution by a constant function. Fourier transform of a constant, the distribution of a constant function is the Dirac delta function, and Fourier transform of the regular distribution with the h in L2 is a regular distribution with the h Fourier transform. We have already some reports about this. Again, thank you for those who made reports. Don't hesitate to do it again, even if there is already a report on this topic you want to study. Doesn't really matter. And then we switch to a new subject. The new thing is just a reminder about Riemann integral, something you do in first year. P, a partition of an interval, so it's a subdivision of this interval into n subintervals. I take a bounded function, and I have defined what is the lower Riemann sum and the upper Riemann sum. And I use these two notation, lower for the function f and for a given partition, and upper. And you have f on an interval, you subdivide. For the lower, you take the lower value of the function in each subinterval. And for the upper, you take the maximum value of the function on each subinterval, and you do the sum times the size of the interval. And we say that it is Riemann integrable if when you take thinner and thinner partition, so you take more and more subintervals, the lower Riemann sum is going to become or equal to the upper Riemann sum. This is a definition of Riemann integrable function. And now this is just a number, but when it's Riemann integrable, but we denote this number by this expression. This is just a notation. And something we see in calculus, continuous function on an interval are Riemann integrable, monotone functions, so functions which are increasing or decreasing, even if they are not continuous, are Riemann integrable. Characteristic function, a function which is like this, is Riemann integrable. So we have at least 3 types of Riemann integrable functions.
A characteristic function of an interval.
Okay, characteristic function on the interval. This is an interval I, and one notation for this function is chi. This is a letter, Greek letter chi, on this interval.
Yes.
It makes it's equal to 1 if x belongs to this interval, and it is 0 if x doesn't belong to this interval. Or you can make something more general than an interval.
If chi of q is not integrable.
I mean, this is always defined. I just define 1 or 0.
Chi of q as in chi of the rational number.
I said an interval. Okay, if you take chi of an arbitrary, no, he's right. Chi of an arbitrary set might not be Riemann integrable if I take an arbitrary subset of R, but I mentioned an interval. Now, this is a good point. If you have any question, you can interrupt me at any time. Otherwise, I continue now with Lebesgue. So this is all for Riemann. Riemann is calculus 1. Lebesgue is already more advanced. So we start with Lebesgue measures. And don't be surprised, some results look simple. They are not so easy to prove. So I start by take A, which is just a collection of n numbers, and B, a collection of n numbers. Real. This is just 2 collections of n number to real numbers. So I define a closed box. It's also called an interval, but it is in Rn, so I don't really like the notion of interval in Rn. So closed box or an interval, and I will denote it. I is defined by it's a set of x1 up to xn in Rn, so it's a set of points in Rn such that Aj smaller or equal to x, j smaller or equal to bj, or j1 up to n. So you observe something when I write this. It's a box. In 2 dimensions, you would have something like this. But it also implies that these 2 vectors are not completely arbitrary. I assume in this definition that Aj is smaller or equal to Bj. Otherwise, it's not meaningful. So I'm not saying I can take any A and B. They have to satisfy this relation. I could write it, but it's written here. Okay, so this is the definition of a closed box. And one more thing in this definition. It's still in the definition. If Bj is really bigger than Aj or Nej, then I'm going to set V of I is just a product j from 1 up to n of Bj minus AJ. And this is strictly bigger than 0. Because I assume that Bj is bigger than Aj. And what is it? It is the usual volume, or yeah, it's volume of I. So you shouldn't be surprised by this. You have a box like this, you take this length times the other length, and you get what we call the volume. Okay? I need this. But now I would like to speak about the volume of a more complicated set, which is not a box. So I need to do something for this. So I need one more definition. What is a covering? So I take a box, sorry, I take a subset of Rn. So suppose this is omega. So I take omega in Rn. A covering, and I give a name to this covering, a covering S of omega. I think I just mentioned this at the end of last week. It's going to be this. Take sufficiently many boxes. This is going to be a covering. So what it is, a covering of omega is S is a collection of boxes, closed boxes. And this is either finite or countable. What does it mean, countable? So let me just say, what means finite? It means J is inside a finite set, 1 up to, let's say, a capital N. This is a finite collection. Countable means J belongs to N. This is the meaning of countable. So S is a covering of omega. If S is a collection of closed box, and omega is inside the union of these boxes, which is exactly this picture. We cover S with a finite or countable collection of boxes or closed boxes. Now, I have I meaning box, but I need this. Okay, this is a notation. Like usually I write this AJ with J from 1 up to N. This is a standard notation, right? It means N AJ. But if I don't know if it goes up to 1 or up to infinity, I'm just saying AJJ, finite or countable. Finite is this solution, countable is this one. And I will repeat this often today. Either it's finite, up to 25, or it's countable, meaning it goes up to infinity, but like N. So this is a notion of a covering. And still in this definition of a covering, still in the definition, we set sigma of S. It's going to be the sum of B of Ij. And again, I don't write J if it is a finite sum or a countable sum, so it means finite or countable. So what is it? Look, I take the volume of this first box, I add the volume of this second box, then I take the volume of the third one here, and the volume of the fourth one here. They overlap, but it's just a sum like this. Yes?
Why did you write that?
So this is a sigma, sorry. Oh, this is a compression of we set. Sorry, we set. Sorry. And this is sigma. This is sigma. It's usually used for kind of volume or things like this. So please be aware that overlap are possible. So it means these, now it's no more visible, but these 4 boxes can be on the top of each other. There is no contradiction. And now what I'm going to do, so let me do the picture again. We had omega. This was omega. As I said, I take covering like this. Okay, let me do a simple picture with only 3. So of course, this is not a good approximation of this volume. So what I want to do is take smaller and smaller covering so that it becomes more precise. So this is the next definition. So definition for omega inside Rn, what is called the Lebesgue outer measure, of omega is given by, or is defined by, we denote it by m star of omega. Who can tell me what to write? Yes, it's going to be the infimum. Don't cheat, don't look at the notes before. Okay, thank you. So the infimum over this quantity, which is what I have just defined, for all possible covering, as covering of omega. So you take all, of course, this is, you cannot do this when you have a, if I give you this region or this subset of Rn, you cannot construct all covering. But you can start by doing some small covering and get a good approximation and try to find the minimal value. This is the idea. Is it clear for everybody what is this definition? Yes.
Why can it not be minimum?
Can I replace this inf by minimum? This is something I haven't explained the difference, but maybe somebody knows why I cannot write minimum and I can only write infimum. Wait a second. Can anybody answer why I need to take infimum and not minimum, and what is the difference? Somebody asked me also in a report. There is a small difference. Let me take the interval. Take the interval 0, 1. What is the infimum number in this interval?
0.
Who said 1? The infimum is 0. So let's say I call this omega. The infimum of omega is indeed 0. What is the minimum on omega? It's 0. Okay, that's fine. Now consider, okay, I should have written it slightly differently. The infimum on this closed interval 0, 1 was the minimum on this closed interval 0. Okay, now what is the minimum? No, first the infimum. Infimum on open interval 0, 1 and minimum on open interval 0, 1. The infimum is 0, but there is no minimum. So this is a difference. This is 0 and does not exist. So wait a second. With this, I'm not giving the definition here, but I give you the feeling. The infimum is really the smallest value, but it can be outside of your set. 0 is not in this set, but it is the smallest value which is on the left of this set, or the biggest value which is on the left of this set. On the other hand, the minimum, by definition, it has to be inside the set. So 0 is not inside, but still the minimum should be 0, because otherwise there is somebody smaller. But the minimum is 0 is not in this set, so it doesn't exist. This is the difference. The infimum can be outside of the set. The minimum has to be inside. That's the difference. So here I'm playing with infimum because I'm not sure that I can find a S so that I get the minimum value. So I need really to, of course, if omega is this box, by definition, this outer Lebesgue measure is going to be the volume of this box. So in this case, I can take the minimum. But if I take the open one, if I take without the boundary, then I need to take the infimum. So it makes a difference. If you are not confident about this, it doesn't really matter. Yes?
Take the open box, contradict the statement, take the closed box.
What you mean contradict? Yeah, but if I take it open, I would have to omega is the open box without the boundary, but by definition, I need to take something bigger. And then I decrease the quantity. So, you can get examples where the minimum is reached, so infimum is reached, and sometimes it's not reached. It depends on omega. So this is exactly why this is the next sentence. Be careful, an infimum is not always reached. So it means there is not always a S which provide exactly the infimum, but for any epsilon bigger than 0, there exists a S covering of omega such that n star of omega is smaller or equal to sigma of S, smaller or equal to n star of omega plus epsilon. So please think about this sentence. I'm saying this is an infimum, but sometimes you don't find a covering which really takes this infimum value. But what you can say is for any epsilon, you can find a covering such that its value is between the infimum and infimum plus epsilon. So it means you cannot always get this value, but there exists a covering which is up to epsilon, the outer measure of this surface. That's a statement. For infimum, you have always something like this. Right. Again, if you have any question, it's quite intuitive. But as I said, for proofs, it's not always so easy. So good properties of M star, of this Lebesgue outer measure. If omega 1 is included in omega 2, it's not so difficult then to guess that the outer measure of omega 1 is going to be smaller or equal to outer measure of omega 2. at least it is intuitive. Take two sets like this. This is fine. This is omega 1. This is omega 2. And you can get this inequality.
It's the same.
Sorry?
When is it actually the same? When one is this open, one is full?
It's really tricky. M star of a union is always smaller or equal to M star of the first one plus M star of the second one. And this is quite intuitive. Be careful, it's intuitive as long as you make nice picture like this. But I'm not saying that omega is always so nice. You can take omega made of, this is still a subset of Rn. And of course, it can contain many, many points. And finding a covering of this and then taking this infimum is probably more complicated than doing it for nice sets like this. So be careful, it's quite intuitive for nice sets. In real life or in the set of all possible subsets, you also have things like this, and it's more complicated. And of course, you can extend this to M star of a finite or countable union. This is finite or countable. Probably I should create a notation for this. But it's smaller or equal to the sum over J of M star of omega J. It's just an iteration of the previous line. Okay. Unfortunately, life is not so nice. No, it's nice, but it would be boring if sometimes you don't have some nasty things. Okay, unfortunately. And you might be surprised by what I'm going to write. Unfortunately. They exist omega 1 and omega 2 inside Rn with empty intersection. They don't overlap, but the outer measure of the union is strictly smaller than the sum. Don't try to get a feeling about this with such a picture, you will not get it. In order to have this kind of situation, you need to go to more nasty sets. But there exist sets with no intersection, so you can, if you think naively, you would say, this situation, this is omega 1, omega 2, and take the outer Lebesgue measure. And unfortunately, there exist sets such that this outer measure of the disjoint union is strictly smaller than the sum. So it means it will not be of this type. Probably these two sets have to be more like this, very close to each other with many things like this. This is more likely a situation. Of course, you have to make it even more complicated, but it's something which is very intricate. So intuitively, you would say, oh, this cannot happen, but it does. Yes. And there is something in the notes about this. I cannot. Okay, I will speak about this a little bit later. So, and of course, this is not something you don't want this. We don't want this. Because it's counterintuitive. So we don't want to have this property. So it means this outer Lebesgue measure, even if it is nice, simple, is not a good notion. We have to change it. So I'm going to give one result, one important result. So it's a theorem. It's not the solution yet, but it gives us a good direction. But let me state a theorem. For any omega inside Rn with m star I'm going to put this statement in parentheses because we can forget it later. So for any set with the outer Lebesgue measure finite, and for any epsilon bigger than 0, there exists omega subset of Rn, lambda open. So if you're not familiar with this letter, this is lambda, capital lambda. Or maybe I should have written this is capital omega. I already mentioned it many times. So there exists an open set lambda such that omega is inside lambda, and I will make a picture. M star of lambda is smaller or equal to n. So what is the meaning of this statement? It's not completely easy. I mean, the proof is not easy. Take a very nasty set, omega. Still, you can, this outer measure is always defined. So we take it smaller than infinity. The statement says there exists a nice set, capital lambda, open, and such that m star of lambda is not really much bigger than m star of omega. It's only up to epsilon. Why do we like red set? Why do we like open sets? Can you guess? I like open sets. Remember the definition of an open set. What is the definition of an open set? Who can answer?
All around any point.
Yes. Take any point, there exists a small ball. So it means locally, an open set looks always like part of Rn. You have really n directions. So locally, you can map a small ball of Rn, which is not the case for this one. I'm not claiming that this one is open, especially if it is made of points. You cannot put a ball around each point. But an open set, so open sets are nice because locally, they look like Rn, or like part of Rn. No, like Rn. Let me say just Rn. Locally, you can really have the n directions. This is why open sets are good. Locally, you can make a parametrization of this nice piece. So we are very happy if any nasty set can be put in an open set, which is just a little bit bigger. This is a rather important theorem. However, you can wonder, there is now one question. The question, what is the measure of lambda minus omega? Look, what is this lambda minus omega? It is this, on this picture, it is this yellow region. This lambda minus omega, on this picture, it is this yellow region. Nah. So observe. This is a question, and unfortunately, we cannot answer it. With this, you cannot, even if you have this estimate, you cannot say anything about this difference, which is quite surprising. So observe that what I'm going to do, I'm going to compute m star of lambda. I'm going to write it as m star of lambda minus omega plus union omega. This is clear. I take lambda, the big set, I remove omega, and I take the union with it. So so I should put a parenthesis maybe. This is just lambda. And now we have seen that the outer measure of a union is smaller than m star of lambda minus omega plus m star of this guy. This is something I mentioned before, and it's always true. So it implied that now if I put it on the other side, we get m star of this one minus m star of this one is smaller than m star of the difference. And this is what we get. And what we know, look, from this theorem, we get that this guy is smaller than epsilon from this. But look, it doesn't tell you anything about this inequality. You know that this difference is smaller than epsilon. You know this difference is smaller than this one, but you cannot say anything about this one. We cannot say anything about this guy. So it's quite surprising, but I mean, this follows from the definition. Even though the open set, the red one, is only slightly bigger than the yellow one, from the definitions we have seen, we cannot say anything about the difference. Is it small? Is it big? No idea. That's surprising. I'm just following the definition. In mathematics, it's a game. You have a set of rules. You use these rules. That's it. Any question or remark? So what does it mean? It means if I cannot control this quantity from the rules I have used so far, I impose a new rule. That's it. Definition. Omega inside Rn is Lebesgue measurable. Is Lebesgue measurable? This is a definition. If for any epsilon bigger than 0 exists a lambda open with omega inside lambda, and now this is the end of the sentence, and the measure of the difference is smaller than epsilon. Yes. So just think about it. What I'm doing, I'm saying that this set lambda is Lebesgue measurable or is good, whatever you give the name you want. It's a good set if the lambda you took before, this open set, which is slightly larger, you can control this difference. This difference is smaller than an epsilon. So it means maybe not all sets are Lebesgue measurables. And indeed, this is correct. If you take a very nasty set, it is not Lebesgue measurable. And still this, in the definition, I need to add one sentence. Still in the definition, if lambda is Lebesgue measurable, I'm going to have, in this lecture, I just put LM for Lebesgue measurable. So LM means, I write it once, Lebesgue measurable. So if omega is Lebesgue measurable, we set the measure of omega is the definition. This looks something stupid, but I just want to say for nice sets, I don't want to keep the star. So for nice sets, which means Lebesgue measurable, I define this Lebesgue measure of omega. It's just a simplification of notation, that's it. So if the set is Lebesgue measurable in this sense exactly, I'm going to put simply M of omega. If it is not Lebesgue measurable, then I need to keep M star, and it's called the outer Lebesgue measure. Okay. Be careful. Sets which are not Lebesgue measurable so sets which are nasty are not easy to exhibit. I gave an example how to construct one in the notes. If you can Google this not Lebesgue measurable sets, and you will see that people are probably giving example, but they are not simple. So it's not easy to find sets which are not Lebesgue measurable. You don't have to do it now. Still keep it for this weekend. But still, we can understand some of them, and I put an example in the notes, but you will see it's not easy. But the good properties. Maybe before the properties. I should have mentioned one or two exercises before, maybe. Oh no, I can still do it later. Let's go on. Open sets are Lebesgue measurable. You can check this. This is almost by definition. All open sets are Lebesgue measurable. So this is what I said before. Open sets are your friends. They are very nice. M star, the outer measure. If the outer measure of a set is 0, we should write if the outer measure of a set is 0, this is already more difficult. It implies that this set is Lebesgue measurable. it's not easy, but it's useful. So if a set with this notion of Houghton-Lebesgue measure is 0, automatically it is Lebesgue measurable, and of course, and M of omega is of course also 0. If omega is a union of omega j, and this is either finite or countable, and omega j is, or are, or is Lebesgue measurable, then the union is also Lebesgue measurable. Then omega is Lebesgue measurable. So it means you can consider a union of nice sets. It's still a nice set. And so it means I can write M of omega, because it's Lebesgue measurable, I can just write M and not M star, is smaller or equal to the sum on J of M of omega G. The same property as before, but it's on, I'm dealing with nice sets. Let me list 2 more properties. And by the way, this is not easy to prove. It's possible to do it, but you can probably not do it just by yourself without looking at a book. I mean, this is, you can understand a proof in a book, you have all the tools, but trying by yourself might be complicated because you have to take this infimum over all covering, which is not an easy thing. Number 4, if omega is an intersection and again, it's finite or countable, with, again, each lambda j Lebesgue measurable, then omega is Lebesgue measurable. But be careful, it's not easy to, you cannot express easily the measure of a set, the measure of an intersection. Think about it, the measure, take 3 sets, intersection. The intersection, which is this part, has almost nothing to do with the measure of the 3 sets. So you cannot express the measure of an intersection easily in terms of the measure of these sets, which we can do for a union. A union, it's quite natural. The union is smaller than the measure of each set. For an intersection, you don't have something similar, but nevertheless, this intersection is Lebesgue measurable. 5, for any closed box I, of course, this is something you should expect. M of I is nothing but what I call V of I at the beginning. So V of I, remember, is just the product, the usual volume. I'm just saying that if you consider such a box, take this Lebesgue measure. It's, of course, what you expect. Yes?
We take the maximum of all measures we have, like countable measures, and intersection must be smaller than the maximum overall.
Yeah, probably yes. But take So one person is asking if we can indeed say something. Yes, but there are counterexample, not counterexample, but let's take in R2 1 omega, which is a half space. So the maximum measure is infinity. Take a second one, which is a small one. So the intersection is this part. So with what you want to say, yes, the measure of this guy is smaller than infinity. This is the only thing you get, which is correct, but it doesn't say so much. So I'm not saying you cannot say anything, but usually you cannot say anything useful. Okay. And the good property which you are dreaming about is for Lebesgue measurable sets, so 6. If omega 1 and omega 2 are Lebesgue measurable with no intersection, then first, we know that this intersection is Lebesgue measurable. Oh, no, sorry. Then, sorry. Yeah, this intersection is, but it's empty. But then we have that M of omega 1 union omega 2. They have empty intersection. This is a picture I made before. Now it's equal to M of omega 1 plus M. Remember, before I said this is not true for arbitrary sets. But it turns out that for Lebesgue measurable sets, and this is why they are important, you get this nice property. Yes, you have a question? The star? No, I said if omega is Lebesgue measurable, then I write M of omega is simply M star. I simplify the notation. So whenever it's Lebesgue measurable, I drop the star. So since I assume that omega 1, lambda, omega 1 and omega 2 are Lebesgue measurable, I can write this. And the union, it's here. Yes, if we have Lebesgue measurable set, the union is also Lebesgue measurable. So I can take the Lebesgue measure of this union. So I can drop the star. Yes?
You're abusing notation.
Ah, sorry. Yes. Thank you. Yeah, it was empty set and not 0, of course. Thank you. So it means for general sets, I define the outer Lebesgue measure, but it has a nasty property that this is not always true. So I take less sets, I eliminate some set. I'm saying a set is Lebesgue measurable if it has a nice property. And for all these sets, we have this. And as I said, finding an example of a non-Lebesgue measurable set is not easy. So whenever you do a picture, this is Lebesgue measurable, no problem. If you want to find a non-Lebesgue measurable set, you have to work. Okay. Let me just state, I didn't do it before, but I can. Okay, let me just keep this last line. Exercise. Show that M star of 0, 1 intersection with Q take all rational numbers between 0 and 1, what is this value? It's not completely trivial. But in order to prove it, you have to use what I just erased. Omega is a union of the set. If omega is a union of lambda, if omega j and each of them is Lebesgue measurable, the measure is smaller than the sum of the measure. So how can you use this information? Take one point, check that the measure of one point is 0. The outer Lebesgue measure of one point is 0. Once you know that the outer Lebesgue measure of one point is 0, you use the property 2. I should have kept it. If this is 0, it implies that is Lebesgue measurable. So once you know that the outer measure Lebesgue measure of one point is 0, it means one point is Lebesgue measurable. We can apply this, and you end up with the fact that since Q is countable, and I'm dealing with countable sets, you end up with this. So please, somebody try to write this. I just sketch it. But you end up with the fact that the outer measure of this is 0, which implies that 0, 1 intersection with Q is Lebesgue measurable with this measure equal to 0, which is something interesting. And we will use it later. So this is one exercise. Another exercise, but as I said, it's not trivial, it's to prove some of these properties. Any questions so far? There is one more property which is useful. What about complement? Okay, this is 6, so I should erase here now. What about complement? If omega is a nice set, so it means it is Lebesgue measurable. This lets us a theorem because it's for omega inside are n omega Lebesgue measurable, then the complement, I hope you remember what is a complement. The complement is Rn minus this set, so the set of points which are not in omega is also Lebesgue measurable. So it means if you have a nice set, its complement, what is outside, is also a nice set. And in fact, you can do the opposite. If you have a nasty set, like this, its complement is also nasty. Otherwise, you would get a contradiction. So this is useful at some point. So really the key point in this theory, and this is why we introduce Lebesgue measurable sets, is that for Lebesgue measurable sets, whenever the intersection is empty, the measure of the union is what you expect with this kind of picture. So it means for Lebesgue measurable sets, what you expect for this picture is true. The measure of the union is a sum of the two measures. But this is not true for arbitrary sets. But you know, all the sets you can draw or you can imagine, it's a very, very big set. Take all possible pictures, it's very, very big. Okay. And as I said in the notes, I wrote one example of how to construct a set which is not Lebesgue measurable, but it's not simple. I don't want to spend time on this. So we know now what is a Lebesgue measurable set. My final aim is to define Lebesgue integrable function. And we will not see them today. I need to introduce one more thing. And next time we are going to deal with integration. 2.3. Lebesgue measurable functions. So in the previous section, we had no functions. It was only sets. I only play with sets, and I define what is a nasty set and what is a good set. Now I want to do something similar for functions. And I can directly give you the definition because we know what is a Lebesgue measurable set. A function f you can see now I'm coming to something much simpler in the sense that I was dealing with Rn. I suddenly go back to interval, so one dimension. I mentioned at the beginning of this chapter, I'm going on in what I remind you last week, it was also the Riemann integral was for function on one interval. You can extend it to sets in Rn. It's not so much more complicated, but the notations are more complicated. So the same for what I'm going to do now and next time. I consider only an interval, and later on I will tell you how to generalize this for Rn. Okay. So a function from an interval to R is Lebesgue, measurable. If for any S inside R, if for any f minus 1 of, I will explain on, no, I directly give you the definition of this. It is a set of X inside AB such that f of X is bigger than S is Lebesgue. So I'll let you write, and I'm going to do a picture. So the first, this notation means exactly this. Look, the set of X, or maybe I do the picture now. See my function? I fix a S. I'm taking the set of X in AB where F is bigger than S. So it means I'm taking this interval and this interval. Look, for all X inside this interval or inside this interval, f of X is bigger than S, right? And I'm saying this set, so this interval and this interval, so this union of two intervals has to be Lebesgue measurable. I mean, this is the definition. A function is Lebesgue measurable if whenever I cut somewhere and I look at the set of points which are sent to this, where the function take value bigger than this fix S prime, let's say, then this either blue set or red set is Lebesgue measurable. And we have seen what means Lebesgue measurable for set. All right. This is the definition. Maybe you remember from calculus 1, K-level sets. It's a kind of, it's related to K-level sets. Calculus 2, right? Thank you. What could I do without you, Vic? Yeah, but many mistakes. I would say many stupid things. Anyway, so definition of function is Lebesgue measurable if whenever we take the set of points where the function is bigger than any S, it's Lebesgue measurable. Example. Take omega inside AB and take chi of omega. Remember, I define this characteristic function, I define it at the beginning. It takes either the value 1 if x is inside omega, and 0 if x is not in omega. So I define this. Then this function is Lebesgue measurable if and only if who can finish the sentence? This function is Lebesgue measurable. So think it's a function which looks like this. It depends on omega, of course. Let's say omega is this two guy. So it's a function like this. So it's here, here, and 0, 0. You see the characteristic function. So this function is Lebesgue measurable if no. Yes, this is true, but you can be more general. No. What we studied just before. No. Oh, yes, this is also true, but this is not general enough.
Oh, wait,
No.
If it's actually Lebesgue measurable.
Check if and only if omega is Lebesgue measurable. This is the only thing which is meaningful. So in particular, you're right if it is countable or if it is open, but you can do something more general. Why? Because look, take any S. Take any S here. What are the set or where the function take a value bigger than this S? It's precisely here and here. And we want this to be Lebesgue measurable, so it means precisely this set has to be Lebesgue measurable. So it's by definition. And if you take a S here, it's an empty set. So the empty set by definition is also Lebesgue measurable. Or if you take a S here, it's everything, and everything is also Lebesgue measurable. Maybe I should have mentioned it, by the way. Okay, just a remark. It's probably stupid, but empty set on Rn are Lebesgue measurable. Probably it's by definition. Okay, so we have at least characteristic function are Lebesgue measurable if and only if the set on which they are defined is Lebesgue measurable. So most of the characteristic functions are Lebesgue measurables. Another example, which is going to play a role, this is 2, as one, now it's 2. I want to consider a function which looks like this. A function which take constant values on some intervals or some sets. But it's not very complicated. So let omega j from 1 up to a certain n inside AB. So I take subset of AB omega j Lebesgue measurable and with the union is equal to AB, but the intersection is empty. So it's like a partition. So I'm just saying that I consider an interval AB, and inside, this is AB, and inside, let's do it with 2 colors. This set, the red one is omega 1. We have an omega 2, let's say here, and omega 3. It's a partition. It covers everything, but the intersection is empty. Intersection. So this is a picture. And a finite number. Be careful, I'm not saying a countable, I'm just saying a finite number. Okay. Now I take also a family of numbers, Cj, j from 1 up to n, included in R. So it means Cj is just a real number. And set F is a sum of Cj j from 1 up to. So please think about it. What does it mean? It means I take a function which has a certain value, constant value on the red part, has a different value on the blue part, and has, let's say, a third value on the yellow part. On every part of omega j, it takes the same value. So it's a function like this. And it's defined everywhere. It's defined everywhere because the union is everything, and there is no point which belongs to 2 sets. So I can really do this picture. This is called a simple function. And the statement is that, I'm still in these examples, this is also a Lebesgue measurable function. Oh, no, sorry. Yeah, it's Lebesgue measurable. And F is Lebesgue measurable. Or a Lebesgue measurable function, which, sorry, I should have written F is a Lebesgue measurable function. And it's easy to see it because again, take any, okay, I should have kept the picture. Oh, I can do it here. Take any S, take a S here, where the function takes value bigger than this S, it is only this red set. But by definition, the red set is Lebesgue measurable. Take a different S. Now, it's everywhere. The function takes bigger values than this one. And you have an intermediate situation where you need to take the union of blue and red. But the union of two Lebesgue measurable set is a Lebesgue measurable set. So it means it satisfies the condition. Okay. So we have two examples of Lebesgue measurable functions. Let me just make a remark. In the definition, we assumed the set of points X in AB such that f of X is bigger than S is the Lebesgue measurable. This is in the definition of Lebesgue measurable function. What happens if you put bigger equal? Or what happens if you put strictly smaller? Or smaller equal? So if you consider the set of functions such that f of X is, let's say, strictly smaller than S. The set of X such that f of X is strictly smaller than S is Lebesgue measurable. We obtain the same set of functions. So with these four solutions, you can, this is an exercise with either this or smaller or equal, we get the same set of functions. So it means instead of from the very beginning taking strictly bigger than S, I could choose any of these four. I end up with the same set of functions. And how do you prove it? Remember, if a set is Lebesgue measurable, its complement is also Lebesgue measurable. So from this, you directly get this one. And now the difference between these two is rather small. And you can do it. I mean, this one is really simple. You have to work a little bit to show that it's equivalent to these two. So it means at the beginning, when I choose this condition, the set of X, so that f of X is strictly bigger than S, this set has to be Lebesgue measurable. I could choose the other one. I would get the same functions, the same set of functions. Yes?
So at the boundary of the omega, what is the value?
They have empty it's no more written, but they have empty intersection. Otherwise, indeed, you need to say something about a point which belongs to two sets.
If they're touching, then
one is open, one is closed. I assume exactly to define a function. You know, if you have a point which belongs to both the yellow and the red, you don't know how to define the function at this point. So I have assumed that omega j intersection omega k is empty whenever j is different from k. Otherwise, you have a problem for defining this function. Yes. So it's rather clear that this function is Lebesgue measurable. And the second remark was I could choose any of this. Okay. We still have a few minutes. Proposition. Let me keep this picture for a second. Back to calculus 1. Maybe you remember, I do a parenthesis. If f and g are continuous on an interval, the sum f plus lambda g is also continuous. The product is continuous. The ratio is also continuous. This is something we do in calculus 1. Okay? And it's not so difficult once you remember what is the definition of continuity. We have something similar here. So let f and g from an interval AB to R be Lebesgue measurable functions with a very precise definition I gave before, which is more complicated than continuity. Then, what is the analog statement? F plus lambda g is Lebesgue measurable, or is, I should write, is a Lebesgue measurable function. It's a Lebesgue measurable. Same for the product. F times g is a Lebesgue measurable function. And 3, f over g, as long as the denominator is not 0, is a Lebesgue measurable function if g of x is different from 0 for all x in AB. Otherwise, you have a problem. Okay. So it's exactly the same statement, but we are not dealing with continuity. We are dealing with this notion of, remember, function is Lebesgue measurable if whenever you cut somewhere, take where the function takes a bigger value, and this has to be Lebesgue measurable for all cut. Then you have to do this for a sum, a product, and a division. So it's not so simple. This is simpler. This is simpler for continuity, but still it's true. Okay. Any question? I'm not asking you to prove this. It's a fact. If somebody wants to do it, it's possible, but it's more work. You need to work a little bit more. But it means I can add two functions, which are Lebesgue measurable. It's still Lebesgue measurable. I can multiply them. I can take a ratio. Now let me come back just to a Riemann integral for a second remark. If f is from AB to R, is Riemann integrable. Okay, I remind you last week is Riemann integrable. I don't want to remind you again what it is. Changing f on a finite number of points is possible. I will explain, and gives another Riemann So what I'm saying here is this: take a function on an interval. Very nice function, continuous function. We know by what I recall it's Riemann integrable. Now change this function. I do it on one point. Instead of taking this value here, I take another value, just at one point. If I can do it at one point, I can do it at 2 points. Now remember the definition of Riemann integrable. It means you take partitions. Okay. In each of them, you take L, F, T. The lower Riemann sum, we take U of L, T, the upper Riemann sum. What is going to happen between the initial function and the new function? On this interval here, the contribution in this interval will be different. So we have the yellow function, which is like this, and we have the white function, which is like this. I just change it on one point. But I'm claiming that if the white function is Riemann integrable, so when you do this partition, you get, when you take the sup on all p equal to inf on all p, if this is true for the initial function, the same is true for the new one, because the only difference is going to happen in one interval. And in this interval, when you make it smaller and smaller, it doesn't count. So this is this sentence. I don't want to be more precise. I'm just saying, if you start with a Riemann integrable function, you change it on a finite number of points, it's still Riemann integrable and you have the same integral. Is it clear for everybody, this? Just think about, you change your function on a finite number of points, so it means the contribution on a finite number of small interval will be different, but when you take smaller and smaller intervals, the difference is going to be negligible. But this is for finite. Can you go up to a countable? Can you change the function up to a countable number of points? So can we change? Can we change on a countable number of points? You should be able to answer this question, not only Vic. So a countable number of points. Can we change this on a countable number of points? Somebody? Why no? Yeah, I gave a function which is 0 on irrational numbers, 1 on rational numbers. And I showed that for this function, we don't have this. So it means the answer is no. And C counterexample I introduced maybe last week or 2 weeks ago. No. C. Let me recall it. F of x is 1 if x belongs to 0, 1 intersection with Q, and 0 if x belongs to 0, 1, but x belongs to 0, 1, but x does not belong to Q. We have seen this function is not Riemann integrable, but I've changed only on a countable number of points. So I cannot extend this to countable. It's not possible. Okay, so this, just remember this. I need to have this in mind. So we want we want to extend. I'm not very precise, but it will become clear later. We want to extend this property to countable sets and even more general sets. So it means this good property of Riemann integral, which is stable on the change of a finite number of points, I would like to make it also valid on a larger set of points. This is one of the aims of Lebesgue integral. Oh, I cannot continue. Very sad. So next time, I need to introduce this AE. What is the meaning of AE?
Almost everywhere.
Thank you. Yes. So next time I need to introduce this almost everywhere, which means the property is going to be true everywhere. It's going to be true almost everywhere with a precise meaning. So we will start with this next time. Do you have any question or remark?